Hello and welcome to our tutorial series about line differential protection. Line differential protection is a core element of line protection and is applied from transmission down to distribution voltage levels. Our tutorial series should give you an introduction and deep insights into line differential protection theory and the Cipotec 5 line protection devices. This session is about device configuration and testing based on an application example for two-end line differential protection. If you already joined one of our last energy automation webinars, you already know the Q&A field on the upper right side in this application. Please enter your questions there. We'll collect them and answer them live in a Q&A session for those who attended the tutorial series. My name is Nina Hühn and I'm technical expert for differential protection. All right, now let us start. Here you see the agenda for this session. I will start by presenting the application example, and then we'll take care of the configuration in Dixie 5. After that, I will upload both devices to our Cipotec 5 digital twin and talk about the basics of line differential protection testing. After simulating an internal fault, we will have a look at the fault records in Sigra. Let us start with the first part, device configuration, a Dixie 5 demo. We will use as an example a 400 kV overhead line with a length of 100 km. There's a line differential protection device at each end of the line, forming a two-end topology. The communication connection is a redundant direct fiber optic connection. The modules used are USAT AV modules. I have already made a device selection in preparation. You can see the product code on the slide. The configuration workflow for the protection communication that I will demonstrate is the so-called Advanced Protection Interface. This slide is an overview about the functional architecture. We have a function group line as digital representative of our transmission line with the main protection function 87L running in it. We have a function group protection communication with two functions protection interface. Each protection interface stands for one of the two redundant communication channels. The protection interfaces are assigned to the channel of the communication module in the device. If you want to learn more about protection communication, you can watch our dedicated tutorial session about it. For our line differential protection to work correctly, it is important to take current transformer errors into account when calculating the stabilization component. In our example, the CT class for both sides is a 5P. Of course, it is also possible to have different CT classes on the different line ends. The table on the slide shows our setting recommendations for the CT arrow in dependence of the CT class. For CT with the class 5P, we will set a CT arrow of 3% for current smaller than 1.5 times nominal current and a CT arrow of 10% for bigger currents. This is a slide with a lot of data relevant for our example configuration. Let's start with the basics. We have a 400 kV line with a length of 100 km. The nominal current is 600 amp and the CT ratio is 1000 amp primary to 1 amp secondary. In our example, I will use the same data for both sides, but it is possible to have different CT ratios on the different line ends. Important is that you have set the same nominal current on all ends. If not, the communication will be blocked. Only if there is a transformer within the protection zone, the nominal current can be different. In that scenario, the nominal power must be equal. Furthermore, you see in this table values for the line capacitance, impedance, reactance, and resistance. With the line resistance and reactance, you can calculate the line angle as shown on the slide. Line angle in this case is 83.9 degrees. Based on the data from the slide before, we can calculate the nominal capacitive charging current of the line. This nominal capacitive charging current is the angular frequency multiplied with the line capacitance, the line length, and the phase to ground voltage. In our example, the result is 103 amp. This value is important for the minimum differential threshold. In our example, I will set the minimum differential threshold to a value of 2.5 times the nominal charging current. Okay, so much about the theory. Now let's come to the Dixie 5 demo. So I already created a new project here in Dixie 5, and all the other steps I will do together with you. So first step, I will create a new device. I will use the product code that I just showed on the slide. And as application template, I will start with the basic template. Of course, we do have application templates where the differential protection function is already included, but yeah, I will do all the work together with you and not use the prepared settings. So press OK and give Dixie some seconds to create the device. So what I like doing at the very beginning of configuring, of creating a project, is the setting to set the correct language and to set the correct setting mode. So do I want to do the settings in setting mode primary or in setting mode secondary? Of course, those two settings can be changed afterwards, but especially when it comes to the language, and for example, you use user-defined signal names, then you switch the language, the names won't be changed in the new language. And for the setting mode primary or secondary, it's easier to start with one setting mode, leave it like that, and don't get confused. So I show you real quick where to find this. So the language settings can be found under Options and Settings. Here, at the moment, it's English, and of course, this is fine for our demo today. And setting mode of the device can be defined in the device itself, here under Settings and Device Settings. So here you have the edit mode and the selection options, primary, secondary, and percentage. I want to do all the settings in primary mode. Okay, so what do we have in this basic template? We already see we have one measuring point for the current, one measuring point for the voltage. We have already one function group line with overcurrent protection running in it, and we have one function group circuit breaker, with the typical control and trip logic. Now, as a first step, I want to insert our main protection function, the line differential protection. So I go to the library on the right side and have to find my 7ST device. So 7ST87. We are on the function for the function group line. And here in this function group line folder, you find the line differential protection. So I insert this by drag and drop to the function group line. Okay. In the theory part, I explained that I want to demonstrate to you the so-called advanced protection communication. And this is the next step I want to do. So also under 7ST87, directly in the first folder, you find the so-called advanced protection communication. Here in this folder, there are two options, type 1 and type 2. Type 1 is for line differential protection. Type 2 is for distance protection applications. So for our example, we use type 1 and also insert it via drag and drop to the settings of the device. In our example, we have a redundant communication. That means we have two communication paths, and therefore we not only need one function protection interface, we need two of them. And this you find in the folder Advanced Protection Only Communication, here in the subfolder Second Protection Communication. And yeah, so the second protection interface is also inserted via drag and drop to my function group protection communication. Okay. Then next step is I want to go to hardware and protocols and to the settings of our USAT module. So here is the USAT module. By double click on it, I open the settings. And here under protocol selection, you can choose for the two channels the protocol that you want to use. In our case, I want to use for both channels the advanced protection interface. The other option here is the classic protection interface. You might be already used to, but yeah, I want to demonstrate the newest technology, of course. Then I use the advanced protection interface for both channels. And yeah, to save from time to time is also always a good idea. And yeah, next step would be to make a connection between our functions protection interface and to the channels of the module. So I go with double click on the first protection interface. And here under PI in assignment, you can choose between the two channels. So in this case, I will connect protection interface 1 to channel 1 and protection interface 2 to channel 2. Okay, so now we have the connection between the function protection interface and the physical channel of the device. The connection that we also can check, or also that we need, is the connection between the function group line and the function group protection communication. So to check this, I go to function group connections, and here to the tab protection function group to protection function group. See, in this example, it's pretty simple because we only have one function group line, one function group protection communication, and Dixie automatically connects them. But it would be also possible to have more than one function group line or to have more than one function group protection communication, and then you can decide here how they are combined. Okay. So we continue with the settings of the protection communication, and therefore I will show you the settings of device combination. So this is also per default available in this function block. These settings you maybe also already know from the old workflow in quotes. Here we see the general settings. So here you decide, okay, which one is my local device? Is it number 1 or number 2? You decide what is the lowest appearing bitrate and the connection mode. So is this device connected to another CPROTEC 5 device, or is it connected to a CPROTEC 4 device? And here you have the options 7SD5, 7SD61, or the distance protection devices 7SA. If you are interested in this CPROTEC 5, CPROTEC 4 compatibility, here we also have a dedicated session about it. In our example, I leave the setting as CPROTEC 5. And I said I want a direct fiber optic connection between the two devices. So I can change here the setting for the lowest appearing bitrate from 64 to 2048 kilobits per second. So to the highest value. Here you see the addresses for device 1 and device number 2. I leave the default values are totally fine for this example. Here maybe new for you is this setting IP address, but this setting is only relevant when you are working with a line diff over IP connection. If not, then you simply can leave these 0 entries in. Okay, then that's all that you have to do for the protection communication settings. Now I want to come to the protection settings itself, and therefore I start with the measuring point settings. So I go to the current measuring point. Here you see the default value is a ratio of 1000 amps to 1 amp secondary. This is what I also want to use for the example. So here we stay with the default values. And yeah, but what we need to change is the CT arrow. Here I showed you this table on the slides. We have a 5P CT class, and for this we have a CT arrow A of 3% and a CT arrow B of 10%. The switchover point of 1.4, this is fine for us. Okay. We can also check the settings for the voltage transformers. Here we see a ratio of 400 kV to 100 volt secondary. So here we are also totally fine with the default values. Okay, next step is I want to go to the settings of my function group line, and here I want to start with the general tab. So here you see the rated values of the line and the line data. The rated current in our example is 600 amp. The rated voltage is 400 kV. And this is the setting what I mentioned earlier. This is very important, that the rated current is the same on both sides. Because if you miss that, if it is not the same, then the two devices won't communicate with each other. Only exception is when there's a transformer within the protection zone, then the rule is that the rated apparent power must be equal. So for the line data, we have the neutral point grounded, and we have slightly different values for the capacitance. So I change this according to the values on the slide. Our line length was 100 kilometer. The line angle 83.9 degree. All right. Then we go to the settings of the line differential protection itself. Double click on the 87 line. Switched already on, this is fine. Yes, we want a one pole operate allowed. So this is also fine. Also the setting for this I differential current supervision. Maybe new for some of you is the setting action on behavior equal test. This is a quite new setting, new feature that we have. For the moment, I will just change it to test local device manually, and I promise to explain later what this setting means. The settings for the remote trip are also, we can totally live with the basic default settings. So here, I don't want to change anything. More interesting are the settings for the I differential sensitive stage. So here the default value is a value of 300 amps. So let me open a calculator real quick. So we said we have a capacitive charging current of 103 amps, and we want to set it to a value of 2.5 times higher than that. So the result is 247.5 amps. So I will change the setting to 248 amp. The setting threshold switch on, this can be an interesting setting for you when there is, for example, a generator connected directly to your line, and during the switch on of this generator, high current peaks can occur, and then it could make sense to make the differential protection less sensitive during this switch on process. Our case, in our example, this is not the case, so I will change it, or I will set it to the same value as the sensitive threshold, and then this setting is not relevant anymore. Our differential protection is our main protection function. When we see an internal fault here, we want to switch it off as quick as possible, so the operation delay of 0 seconds is fine for us. Here we have the IDIF fast 2 stage. The IDIF fast 2 stage is an improved stage compared to the IDIF fast stage, and it was optimized when it comes to CT saturation. And here it is important for you to know that this IDIF fast 2 stage is only available in our CPOTEC 5 modular devices. That means when you are working in a combination CPOTEC 5 modular to CPOTEC 5 non-modular, then you have to delete this stage and insert instead the IDIF fast stage. Same is valid when you have a combination between CPOTEC 5 on the one side and CPOTEC 4 on the other side. Because the IDIF fast 2 stage and the IDIF fast stage are not compatible with each other, and this will also lead to a communication problem between the two devices. Okay. The setting recommendation for this IDIF fast 2 stage is to set the threshold value to 1.2 times nominal current up to 2 times nominal current. So we can also do a quick calculation. We had a nominal current of 600 amps. If we multiply this with 1.2, the result is 720. 2 times nominal current would be 1200 amp. So with a setting of 1000 amp, we are totally fine within this range. So I will leave the default value of 1000 amps here. Okay, so much about the settings for the line differential protection. Next step is take a quick look to the settings of my overcurrent protection. Per default, the setting for the emergency mode is no. This setting I want to change to caused by main protection for both overcurrent protection functions, simply for the reason that as long as my line differential protection is active, we won't get an overcurrent trip, and this is makes the testing easier later on in the digital twin, that we don't see a trip from the overcurrent protection that we don't want to see. Okay. Then next step is I want to take a look to the information routing together with you. And here, talk about some important routings. One would be that you should always check how the measurement values of the function group line differential protection are assigned to the record. And specifically hereby I mean the settings of my IDIF sensitive stage. And here you see the measurements for IDIF and the I restraint values, and they should be assigned to the recorder here. Because later on, when you have a fault in the network and you want to do a fault analysis, this is a lot easier when you have these measurements here. Also, it makes sense to see pick up and operate for the IDIF and the IDIF fast 2 stage. You see at the moment here, these signals are already assigned to the recorder, and this is a Dixie feature since Dixie version 9.60, that even if you insert the function newly from the library, to the device, then these routings are done automatically. But if you are working with an older Dixie version, or simply want to make sure that it is assigned, then you should check this routing in the matrix here. Okay. So next thing is I want to do some routings for the binary inputs. At the moment we do see some default assignments for the circuit breaker. So it's, yeah, the circuit breaker position and so on, but they are not interesting for me in this example. So I delete them to have more free space. And what I want to add are connections for switching the test mode on and off, or switching the different test modes on and off. Because I want to explain to you what test mode options do we have in ZProtect 5 line differential protection. First thing you found here in the folder general, and down here test mode on, test mode off. Those two signals I assign both to the binary input 1.1. So test mode on I assign with high active, test mode off I assign with low active. Of course, it would be also possible to use two different binary inputs. So here you are free. All right. Then I go to our function group line and to our 87 line differential protection. And here also in the tab general, maybe I make this a bit bigger. Okay, so here is the option test local device on, test local device off, and check operation point on and off. And those are already also interesting for our test. So I assign them to binary input 1.2 and binary input 1.3. Okay, so much about this. Then in preparation, I created a display page for the different test modes, because this makes the demonstration later on maybe a bit easier for you, or easier for me to explain what I mean. So I will import this display page that I created. So here I called it test mode. And it includes here one display page for the test modes. Use the import option here. And now on the display pages, you see we have the default page with the operation values, and we have a display page for the different test modes. Okay. Then yeah, one more step. I go to hardware and protocols, and here to the settings of my port J. This IP address I changed to a different value. Give me a second, and then I explain why. Okay, so later I will work with our digital twin, and I want to establish a VPN connection to the digital twin. And for this, I need the IP address to be in a specific range that the communication can be established. And this is in my case here, this IP address. All right, then we are finished with the configuration of our first device. Obviously, we need two devices, but don't worry, we won't start from the beginning. So I simply copy the first device and paste it to the very same project. Okay, here we are. So we have our 7SC87 1 and 2. Now let's check what needs to be changed to establish a communication. First thing is I want also here to change the IP address for port J, because it's not good when they are having the same IP address. And then I want to go to the settings of my protection communication, and here specifically to the settings of device combination. Because here now we are in our second device, so we need to define this here also in the settings that my local device is device number 2. If both have a value of 1 here, they also won't communicate with each other. Okay, yeah, and that's already all we have to do in Dixie. So I export the whole project to Dixie, to the digital twin, and our digital twin is working with the so-called SIM file format. So this is the last one here in this list. And here you can also define the export content. For example, if you are exporting a bigger project, then you can decide, okay, which of those devices I'm interested in. In our case, of course, both of them. It would be also possible to export them separately. So this is just a little bit quicker. And I save this file on a place where I can find it again and use the export option. Okay. In the meantime, I switch to the digital twin. So here I already logged in to our ZProtect 5 digital twin website. Here under project and device list, you see the already uploaded devices. So here simply the test from my last try run last week. So here we need to exchange them with the new files. And you can do that by using this plus SIM button here. We see if Dixie is already finished. I think not yet. Yes, and now we are finished. Okay, so I will upload the file we just created. Use the option replace here, because I'm not interested in the old ones. And here we also need some seconds. Okay, here we are. So I choose all devices here and use the option start simulation of selected device to switch them on. In the meantime, I would like to explain to you with some slides what we are planning here in the next part of this session. So we come now to the part functional testing, ZProtect 5 digital twin demo. First thing I want to test is a scenario with normal load conditions. So here that means we have, in this example, a current of 1 amp secondary flowing through the line. And I want to explain to you how we calculate the restraint current in this case, and how to inject this value. A current which is flowing through means always, for the first CT here on the left side, it looks like the current is flowing towards the line, towards my protected object. So this will mean a positive angle, positive sign of 1 amp. For the other CT, this current is flowing like away from the line, away from the protected object. In this case, we have a current of minus 1 amp or with a negative angle. Below this little sketch, you see the formula to calculate the restraint current. We see four terms here in this equation. First one is the threshold, the minimum differential threshold. Second one is the part where we consider the CT errors. The third part is a term to consider the signal distortion. And the last part is there to consider synchronization problems. Okay, let's do an example calculation. Our threshold value was a setting of 0.248 amp secondary. So this is like a fixed value. The second term here is there to consider the CT arrows. Hope you remember we had the CT arrow A of 3% and the setting CT arrow B of 10%, and a switchover point between them of 1.5 times nominal current. When the current is below this 1.5 times nominal current, then we are working with the 3% value. When we are above, we will work with the 10% value. In this case, our 1 amp secondary is below. That means we are calculating here 1 amp multiplied by 3%. And we not only have one CT, we have two CTs on both sides of the line. So we need this factor 1 amp multiplied by 3% twice. The result is a value of 0.318 amp secondary. This secondary value must then be converted into a primary value with the ratio of the CT of 1000 amp to 1 amp, and the result is 318 amp primary. Differential current and restraint currents are always displayed as percentage values, and percentage values related to the nominal current. So we take our 318 amps, divide them by our nominal current of 600 amp, and the result is 53%. So now I want to show you in the digital twin if our calculation is right. All right. So I hope in the meantime our devices are started. Yes, this looks good. So here we have our two 7ST82 devices already running. We see only one LED is on. This is the LED for that our circuit breaker is in an intermediate position, because I deleted all the position routings, so we can simply ignore this LED here. These inputs here can be used to injecting currents to our simulated device. And here I will inject nominal voltage, so this is already fine. And the secondary value current of 1 amp. And with 0 degree on the one side and 180 degree on the other side. And then we apply this value. And we see here now voltages and currents are injected. And to show you the measurements and to show you the restraint and differential current that the relay calculated, I want to establish a VPN connection to the digital twin and show you these values in our Cybertech 5 web browser. So I create a new VPN password, use the SoftEther VPN client to connect to the digital twin with the new password. Okay, and that's all. And then I simply enter the IP address of the device, of my port J in this case. And okay, this time I typed it right. Okay, so we go to the IP address 192, 168, 200, and 101, what I just configured for my port J. This is the login window to the web browser. Here I did not change the password, so it's simply the default one. And this is the interface of our web browser. This is a pretty nice feature that we have, because here you can simply check everything in the online device without having to use Dixie or to open Dixie. You can check the logs of the device. You can download recordings. You can check if there are any alarms, for example. Which functions are active, which are not. And you can even change settings if you want that. You can also define by setting that it should not be possible to change everything, but the tool is capable of doing it. Okay, and together with you now I want to go to function values and here to our line 1. Here's our 87 line differential protection and the sensitive stage. And luckily we see almost what we calculated. We calculated a value of 0% differential current, of course, and of 53% restraint current. The slight difference is because in this equation, maybe you recognized it, I ignored the parts about signal distortion and synchronization errors. So maybe this is this 1% inaccuracy here. All right. Now I want to do a second example calculation. So here I prepared again a slide for this. Second example calculation would be an external fault condition. External fault means the current is still flowing through the line. We see no differential current, but the restraint current is bigger because the current which is flowing through is getting bigger. Because this is a fault current flowing towards the fault through the line. Here's the same equation as before. Of course, the threshold value also same as before, our 0.248 amps secondary. But yeah, main point on this slide is that this time when we have current flowing bigger than 1.5 times nominal current, then we have to use this CT arrow B, so this 10% for the CT arrow. That means this time we use the 3 amps current flowing multiplied by the 10% CT arrow, and this also twice, since we measure this current in both CTs. Then the result is a little bit a bigger value of 0.858 amps secondary. In primary, this means 858 amps. And if we set this in relation to the nominal current, the result is 143%. And of course, I want to show this to you in the digital twin, if also this calculation fits. So we simply increase here this value from 1 amp, to 3 amp. And I apply this value to the device. See, now the value is getting bigger. Let's check in the web browser what we see. And we see a value of no differential current and a restraint current of 145%. Again, we ignored the parts of signal distortion and synchronization problems. And even the digital twin has a small difference here. So we have almost reached our calculated value. All right. Next step is I want to show or to explain to you the different test modes that we have in ZProtect 4. And for the different test modes, I have again prepared some slides. Yeah, now I want to explain to you the different test modes that we have, and therefore I also prepared some slides. First test mode is the setting test mode of all devices. Here we have a setup. You can have a setup in mind like it is shown on the slide. For example, you have the two devices staying on your desk in your laboratory, and you have two Omicrons connected to each device, and the two Omicrons are synchronized with each other. In this test setup, you switch the test mode on in all devices, and you can execute a very comprehensive end-to-end test where you inject currents in both devices and check if the line differential protection is working as it should. And here you have also the option to decide by setting should the binary inputs and outputs get active or not. So if the function trips, do I want to see this trip in the binary output or not? And in this test mode, all signals are flagged with a so-called test bit. That means in your substation control system, you can see, for example, okay, this is a test. We can ignore these values. These are not real fault conditions, something like that. So to activate this test mode, you first need to check the setting action on behavior test. Then you activate the test mode in both devices, and then you are good to go. So let me show this to you. First in Dixie 5 again, where you find this setting. So when you go to the 7SD87 and here to the function group line and to a function line differential protection, here is the setting action on behavior test. There are two options: test local device automatically or test local device manually. If you choose the setting test local device automatically, that means as soon as you switch on the test mode, it will directly jump into this test local device test mode. If you want to do this whole comprehensive testing with all devices of the topology, then you need to choose the option test local device manually. I hope it gets clearer when I have explained both test modes to you. So in our case, the setting that we choose is test local device manually, and this is the right one for this full comprehensive end-to-end test. Okay, so I go back to the digital twin. I will reset the currents real quick. And then I go to the binary inputs. Here are the three binary inputs that I configured. First one for the test mode of the whole device, second one for the test local device, and the third one for the check operation point. I start with the test general mode on for both devices. So activate these checkboxes here and send the information towards the device. Okay, what we immediately see here, now we have an LED, a second LED, and this is called functions in test mode. This is like a default LED, default connected LED, which should make you easier to not forget to switch the test mode off. It means when you are on site and do some testing, then you should also check that the test mode is switched off when you're leaving, and therefore we have this LED. So as long as this is on, then any function in the device could be in the test mode. So I prepared a display page for the different test modes. And what we see now here is the line differential protection is inactive off. That means it is still active. Of course, it should be also active if we want to do these comprehensive end-to-end tests. We do see the binary input test mode is on, and we do see the information yes, there are functions in test mode. Same is valid for the second device. Here also, line differential protection is active, test mode is on, and here also the information is also the test mode in the remote device on. Okay. Yeah, now you would be good. You are ready to do your tests, whatever you want to do. Since the tests would be the same as I showed you before, it makes no sense to show everything again. So I will switch again to the theory, to the slides, and show to you our second test mode that we have. This is the so-called test mode local device. So here the idea behind it is that maybe the devices are already installed. There is a huge distance between them, but you will do a last check. Okay, is my differential protection running? Is everything fine? Then you can also only connect to one of the two devices, to the local device that you have, that you're sitting in front of, and connect only this device to the Omicron, and then activate the local device test mode. And in this test mode, all locally injected test currents are seen immediately as differential current. And here we'll also do a little example calculation that you understand what I mean. So what I will do now is to switch on the test modes of one of the two devices and inject 1 amp to this device. Here you see again the formula to calculate the restraint current and the formula to calculate the differential current. We start with the differential current. As I said, everything what I inject locally will be immediately seen as differential current. So this is our 1 amp in this case, and 1 amp secondary means 1000 amp primary. 1000 amp primary in relation to our nominal current of 600 amp is 167%. So in this test, I will expect differential current of 167%. How big is the restraint current? Here, again, there's nothing changed for the threshold. So the threshold value is 0.258 amp secondary. We are injecting 1 amp. That means we need to calculate with CT arrow A, so the value of 3%. But this time, important, we only inject this to one of the CTs, not to both. So here we don't need this factor 2. So we simply have 1 amp multiplied by 3%. And the result of the equation would be 0.288 amps secondary. Set this in relation to the nominal current, and the result is 48%. So we expect a restraint current of 48%, differential current of 167%. Always wrong. Okay, then I will show you this in the digital twin. Or before I show this in the digital twin, I jump real quick to Dixie, again to this parameter. So when you have set this parameter here to test local device manually, that means you have to do 2 steps to activate this local test mode. First step would be to activate the test mode for device. Second step would be to activate the local test mode. If the setting here is configured as test local device automatically, then you only have to switch on the test mode for the device, and he will automatically jump to this local test mode. So here, whatever you choose here, this depends on what tests you want to do, what tests are you regularly planning to do. Okay, in our case, we have this setting test mode manually. That means we have to do 1 step more. And this I want to show you. So we start freshly without any test mode. And then first step would be to activate the test mode. Maybe it's also interesting to see what happens then if we activate the test mode only in one device. Then we see now our line differential protection is inactive on, so it is blocked. Here on this device is the test mode on, but on the remote device it is off. And for the second device also 87L is inactive, test remote device is on, but this second device is now not in test mode. So whenever you only switch one device in the test mode, this will lead to a blocking of the 87L. But in this case, I want to do only this local test, so I additionally activate this test local device. Okay, and then we see it is getting inactive off again. That means our line differential protection is active again. Test mode is on, local test mode is on, and the test mode in the remote device is still off. For the other device, the 87L still inactive. But of course this device reports that the test mode in the local device is on. Here the line differential protection is inactive because when I'm doing tests with my 7ST87.1, then I want to avoid to see any malt drip, any operation in the second device. So I can do whatever I want to do with device number 1 without having to worry that, both devices will trip. Okay. So let's inject some currents, and I said I want to inject 1 amp to the local device, and we see a trip, and the values that we see are differential current of 167% and restraint current of 48%. So this is what we calculated here. So we see, okay, the device has tripped, we get all the messages, but all messages will be also in this test mode flagged with this little test flag, so that you can see in your substation automation system, okay, don't worry, this is only a test, not a real fault. And no binary signals, binary outputs are getting on, only if you want them to get on. So this can be decided in the configuration. Do I want to get the binary outputs to get active or not? All right. Last point that I want to show to you is our third test mode. So here, again, back to the theory real quick, back to the slides. And this is the so-called checking the operation point. Here the idea is that both devices are already installed, both devices are already connected to the CTs, and there's even a current already flowing on the line. And then we have this so-called check operation point test mode to do a last checkup. Okay, are my values plausible? With this current that is flowing, does the restraint current make sense? Does the differential current make sense? Is the function running? Do I see the communication? Is the communication running? So this would be like this last final check before going live with your system. And here this is not for testing anymore. So this is only for this final checkup. And here the line differential protection remains active, but no operate indication are generated. And to get in this check operation point mode, you activate the check operation point mode via binary input, for example. And then this function or this test mode in a remote device will automatically get active. So here you only have to switch it on in one device. Second device will follow in the same test mode. Reason for that is that here, we expect, okay, there's already 100 kilometer of distance between the two relays. Maybe you have no chance to activate it to communicate with both devices. So you switch it on in your local device and the remote device will follow. Let's give it a try in the digital twin. I reset my fault here. A quick 0 current. Okay. So I will start again with no test mode. And then we will activate for the 7SD871 this so-called check operation point on. Now we see here the binary input check operation point on is on, and we get the information, okay, the check operation point is getting active. My 87L is inactive off, so here, line differential protection still running. Let's have a look at what happens for the other side. So here, of course, also 87L is running, and here we see, even though this binary input signal check operation point is off, the mode itself is activated because we activated it on the device number 1. And in this test mode, you can again go to the web browser. Okay, are the values plausible? Is the communication running? Is everything fine or not? All right. Now, this was all what I want to demonstrate you in the digital twin. Now we come to the last part of the session, to our fault analysis in SIGRA. Here, one last step in the digital twin. Here I want to simulate an internal fault fed from both sides. That means here the current is flowing from both sides towards the fault, which would be clearly an internal fault. And then we will download both records and have a look at them in SIGRA. Okay, so let me jump back to the digital twin. And we start with normal load condition and then simulate this fault condition. So we start with 1 amp on both sides, and then I will increase the current on both sides and change the angle from 180 degree to 0 degree. That means, I forgot one little thing. Let me go back to the normal load currents because I forgot to send them to the device. So okay, now the device is running with the normal load condition. Now I will increase the current on both sides and change the angle. Changed angle means now both have a positive sign or an angle of 0 degree. That means both currents are flowing to my protected objects, to my line, and this would be a clear fault. So we expect the device to trip, and yes, this looks good. So I go back to 0 current, and let's take a look at the fault record. So to go to the fault record, I go to the home page, to the home button again, and here to the tab recording. Here are our 2 records, the one from the test local device and the one we just created. So I take the one with the newest timestamp and use the option download the selected fault record. I have to allow this download here. Okay, that's it. Then I will connect to the second device. Herefore, I just need to change the 101 to a 102. And also here I go to recording. Here we only have one record from the fault we just tested. And I download here also this selected fault record. I allow this download. Okay, and then we can take a look at it. So here we see the two records that I downloaded, and now we want to see, how does this fault look like in SIGRA? I start with the first one and zoom in a little bit. All right. And the first thing I want to show you in SIGRA is to measure the time between the fault inception and the trip signal. So the fault starts somewhere here. The trip signal is here. And when we scroll down and check what happens here with the trip signal, you see here this blue cursor line is the pickup and operate of my iDiff fast 2 stage. So this was, of course, as the name already says, the faster one of the two stages. And when we measure the time between fault inception and the trip of my iDiff fast 2 stage, the time difference here is 5.2 milliseconds. So this iDiff fast 2 stage is pretty fast, I would say. And here pickup and operate come to the same time because, here it makes no sense to have any operation delay when it is a clear high current internal fault. The iDiff sensitive stage, you see, is a bit slower, so it comes some milliseconds later. So if we measure the time here between fault inception and the pickup and operate of my sensitive stage, the time difference is now 25.2 milliseconds here. We are, a lot of faster with the iDiff fast 2 stage. So what else can we see in the SIGRA record? We can take a look at the I differential and the I restraint currents for this fault. And to make the analysis easier, it can help to have the differential current and the restraint current within one diagram. So you can scroll down to the restraint current of my phase A, and simply by drag and drop, you can put it in the same diagram as my differential current for phase A. And then, of course, we do the same for phase B and phase C. And let me make one of those diagrams a little bit bigger to make it easier to see. Then, what do we see? We see at the beginning, so before the fault, where we had these normal load conditions, then, of course, there's no differential current. And then at some point, the differential current is getting really big. So it jumps from 0 to, 1, very, very big value. For the restraint current, we start with a value of 50.3%, then it gets 0, and then it gets to a bigger value of 145%. So maybe now you ask yourself, okay, why is it 0 here? Why do we have no restraint current during the fault inception? And this is simply because if the relay detects a jump, then during this jump, my sensitive I differential current stage will be blocked. And we don't have to worry. During this blockage, of course, my iDiff fast stage is active. And if it is a clear internal fault with a high current, the idle fast will immediately switch it off. This is exactly what happened here in this example. But for the sensitive stage, we want to make sure, okay, even the fault is somewhere at the border, if it is a fault or not. We want to make sure that we have a clear measurement. Therefore, we block the sensitive stage for one time period here, for 20 milliseconds. If you want to learn more about the theory, the algorithms behind line differential protection, we will also have a session about it. Okay, so for analyzing a differential current fault, it also can make sense to not only watch at the local current, but to take a look at the currents from both sides. And here SIGRA offers the possibility to open a second fault record. This can be done here in Insert and Record. And here I open the second one. We see now at the top both are open, and first one is marked with K1. The second one, for all in front of all signals, you can read K2. And here I also want to put the currents of both sides for each phase within one diagram. Of course, this can again be done with this drag and drop, as I demonstrated for the restrained and differential current, but this can also be done by using this matrix here. I know it's a bit hard to read, I guess, but here we simply assign in the same diagram as K1, first current is assigned, we assign the current for phase 1 of the second side. And this we do for all currents here. Okay. And yeah, this is how it looks then. You see, before the fault, the currents have an opposite angle, an angle of 180 degrees. And as soon as the fault starts, the angle in one of the two current transformer changes. We are now measure a current that is in sync for both sides. And in sync for differential protection is never a good sign, always a sign for an internal fault. So here we see clearly this is the fault condition, this is the pre-fault condition. For this record here from my simulated test case, the records are like the two records are like perfectly in sync. In real time, it can happen that it doesn't look like this when you open two records. Then SIGRA offers the possibility to manually adapt the synchronization. So if you open it and you see some kind of shift between the two records, you can adapt this. And of course here it already is perfect, but I want to demonstrate you the steps how to do it if this is not the case. And this can be done here by Edit and the option Synchronize Fault Records. But let me do one thing real quick. Okay, so with this synchronized fault record, SIGRA will shift one of those two records by the time difference that is between the two cursors. So in this case, we have a difference between 1.443 milliseconds. That means SIGRA will now shift one of the two records by 1.443 milliseconds. And we can take a look at how this looks like. Of course, whatever you do in SIGRA, you never know what happens in the real world. So you don't know if the relay are perfectly synced or if there is a little bit time difference between it or not. But yeah, the fault analysis itself is easier when you start with like perfectly synced conditions to understand what happened. Yeah, and this is then how this can look like. For example, when you open two records, you see, okay, there's somehow a shift between the two records. They are not fitting together. Then you can use these options, synchronize fault records. And then it should look like this. Okay, so now I just showed you. I made it worse to make it good again. And this is how it's done. And yeah, now we are finished. We are at the end of this session. I hope you liked it. I hope you enjoyed it. Thanks for your attention, and looking forward to see you in one of our other sessions. Have a nice day.